Hi, everyone, and welcome to the Chem Lab. In our last episode, we spent some time writing formulas for simple ionic compounds that were very predictable, where the metal ions have only one possible charge, and we had to balance those charges. In this episode, we're going to tackle these sneaky transition elements who have decided that it's their job to make things a little more complicated for us. Not that much more complicated, but just a little bit because they have more than one possible charge and we have to deal with it. So grab your periodic tables and let's get into it. And here is our chart we've been using to organize the four different types of ionic compounds. There's two different types of metal ions. There's regular metal ions and transition metal cations. And there's two different kinds of anions. They're monatomic, one atom each, or polyatomic, which are groups of atoms. In our last video, we spent some time up here in this combination using traditional metal ions and monatomic anions. Today, we're going to kick it up a notch and do transition metal cations and monatomic anions. So we're going to do this diagonal situation. Okay. And before we get going, you are going to want to get yourself, if you haven't already, some sort of periodic chart of ions or some resource that will tell you the different charges of the metal ions. Maybe your teacher has already given you one, and that's great, wonderful. If not, go Google this periodic chart of ions or transition metal charges, and you're going to get millions of resources out there. Your job, hopefully, is not to memorize them all. I never make my students memorize all of these. We just use the tools that we have, and this is one of them. This is a typical one. You can get a different one. It's fine. Okay, and just a reminder of what we did last video and what we're doing again. To write the formulas for ionic compounds, what you want to do is determine the charge on each ion. Those transition elements have more than one charge, so we have to figure out which one we have. Hopefully, thankfully, it's easy. Use as many as you need to make the total charge for the molecule 0, and add subscripts to show how many you used. All right, so if something has more than one possible charge, how do we decide which charge are we actually using? Thankfully, if we have the name of the compound and it's written correctly, it will contain a Roman numeral. And that Roman numeral tells you the charge of the metal ion. It doesn't tell you how many of them there are. It's not like there's 3 irons here, but it will tell you that it's iron 3 plus, not iron 2 plus, not iron 6 plus, but iron 2 plus. Okay, so let's take a look at this thing again. Iron does have, in this case, more than one charge, so +2 and +3. There is a +6. A resource like this sometimes just gives you the two most common ones, but there's a lot of options out there. But the Roman numeral is going to tell us which one is which. So we have iron 3 iodide. So let's just take a moment and write down the charge, Fe plus 3. Okay, and then the iodide, looking at our resource, has a -1 charge. So Fe plus 3, iodine 1 minus. And just what we're going to do, same as last time, we're going to swap those numbers, and they will become the subscripts, Fe1, I3. Okay, and that balances 3 positives and 3 iodines at 1 each will give you 3 negatives, and that will balance. So make sure that that's in reduced form, which it is. Okay. All right, let's do another one. Lead 4 oxide. Lead can be a +2 or a +4, just because. And what we're going to be doing is using the +4. So we're just trying to get in the habit of just writing it down, not having to worry about it. +4 and O and -2. So let's first do the shortcut where we cross those charges to get the subscripts. So Pb2O4, which is pretty good. We're on our way. But we do have to perform an important test. And the test is this in reduced form? And the answer is no, it's not. 2 and 4 are both divisible by 2, and so I can reduce that to a 1 and a 2 right there. So make sure you're checking to reduce it if at all possible. Another way to think about it, if you think about it visually, if you have lead 4 and a -2, you might notice that 2 goes into 4 2 times. So really, all we need is actually 2 oxygens to balance that +4 with a -4 charge. And so it ends up being PbO2 if we do it that way as well. So just remember to reduce it if you can. All right, a couple more, and I'll have you try our pause the video moment. All right, let's do chromium 3 phosphide. Chromium, no, that's 2, sorry. Chromium has a 2 or a 3. In this case, it's a +2. And phosphide is in the same column as nitride on our chart. And you would see that that has a -3 charge. So I have a 2 trying to balance with a 3. So a 2 and a 3, cross them over, is going to become a 3 and a 2. And that cannot be reduced, so we are good with that one. And then the last one is nickel 2 oxide. Nickel is a +2. Oxide is a -2 according to our periodic chart. And again, we can see that they're the same charge. Now we can swap them and make it a 2 and a 2 and then drop them to a 1 and a 1. Or I can actually just know that those are going to balance, no problem already, and just make one of each. Okay, so nickel oxide. All right, and now it's time for our pause the video moment. I have 2 more here. Take a moment, pause the video, and see if you can write the correct formulas for those 2. See you here in a couple seconds. Okay, and if you were able to get these 2 formulas, for gold 1 sulfide is Au2S, and niobium 5 oxide is Nb2O5. You may have to review your Roman numerals. I don't know if your resource that you're using has Roman numerals on it, but you may want to know what those are. So if you didn't know that the V is 5, that would be something to refresh on. But here we have it, writing binary ionic compounds with transition elements. And I hope you found it helpful. If you have a question, send it to me in the comments. And in the meantime, happy studying and have a great day.